All right, so in this video, I'm gonna just do an overview of the code for both the Arduino and the Android app side of the logging scale project. So I won't be quite as detailed as in my last code review for the previous Bluetooth connected scale, simply because a lot of the code from that project is duplicated here. So for instance, if you're interested in how the HX711 programming works or the BLE connection, how to send data back and forth from the microcontroller over to the app, I'm not going to go into a lot of detail here because I've kind of already done that in that previous video. So to start off in Arduino, I've got my includes all up here. And again, I'm using the Xiao ESP32-C3 model. I'm also using a different OLED screen than I did in the previous project, and I had to use a different library, so I'm using the U8G2 library to drive that display. And so starting off in the initial stage, I'm setting up the display and defining some functions here for the display. And so I'm just setting up the 128 by 64 pixel OLED over an I2C connection. And then I've got some functions to get the display width and do some alignment just to make things display on the screen without having to do this every time I want to run something over the screen. Then we've got a section of variables that are all for the load cell. Again, I covered that mostly in the other video, so I'm not going to spend a lot of time explaining here. I've got 3 buttons on the case of this model. I've got the sleep button, the tear button, the units button, so I'm just setting them up there. And I found that the units button, it needed to be debounced because every time you push it, it would make multiple connections and it would flip the units without being reliable. And so I've just got some variables set up here that will be used for debounce settings. And basically all that is just some timers to make sure that the button doesn't flip states before a set amount of time has passed. That way, again, it slows down the responsiveness of that button. Then I've got my characteristics for the BLE service and the characteristics to send the data over. One thing about the way I built this app, and it probably isn't the best way to do it, but it's just the way I did it, is that I actually send the mass over to the app in 2 different ways. So I've got this mass characteristic here, and this is the main data stream that goes to the big display in the app. And then I've got a logging characteristic that only fires up whenever you do the logging. And the reason I sent it over 2 different characteristics is because I don't want to log as fast as possible. I want the logging data to be sent at precise intervals. And so I couldn't really think of how to do that except for to split the data into 2 streams. So the mass characteristic is going to be updating kind of live as soon as data becomes available. The logging characteristic will update at a fixed timed interval, and that's set right here. And so here you can see I've got the BLE mass variable itself, and then I've got a logging state indicator, and I can tell the microcontroller, hey, if this log state is 1, then I only want you to send the data to that portion of the app. And here I've got it set to every 250 milliseconds, so 4 times a second. This also meant that I didn't really have to do much on the timing side in the app itself. Because the microcontroller kind of runs in real time, I'm going to know that any data that I receive over this logging channel is always at 250 millisecond intervals. And so on the app side, I don't actually need a timer. I just know that every sequential value is 1/4 of a second since the last one, and I don't actually need to time when they come in because I'm only sending them that frequently. And so that timing is as precise as the microcontroller is because that's how it initiates the data feed. And so in that way, I was able to avoid more problems with timers and things. Okay, next we get into the setup, and again, most of this is, just basic stuff. So I've got, buttons set up for pin modes. One thing is I'm only defining 2 button pin modes here, and that is because I ended up putting an external pull-up resistor on the sleep button, and I'll talk about why in a minute. I ran into some problems with the deep sleep function, and I thought that it might be related to pull-up resistors because I'd read a bunch of stuff trying to solve that problem. I don't think that ended up being the case, but some people said that this version of the ESP32 kind of had some problems with the input pull-up resistors in the deep sleep process. Again, I don't really think that was the problem that I had, but I put that resistor on anyway. Okay, then we've got, again, just some startup for the scale and just some things being written out to the display. We then, here I'm defining out a pin mode for reading voltage. One of the other things that I ran into as a problem is that, I wanted to run a battery, and, you want to know how much battery you've got. And whenever you read about the SEED Xiao, you got to be careful because there's multiple different versions. And I was reading some stuff, and it was all about, reading and which pin you can find internally to read the voltage from the battery and stuff. But that apparently only applies to the Nordic version of the Xiao, or maybe, one of the other ones. But the ESP32 version of the Xiao doesn't have an internal pin to read the voltage of the battery. So what I had to do is bring in the voltage over an external pin, and that is coming from a voltage divider. Again, you can watch the build video to see that. I'm using two 200K resistors to do a little voltage divider and reading the middle value there. And so this is the pin that it comes into for the ADC. And so when I'm doing that, I am making sure that I use one of these analog input pins. Again, there's a limited number of pins because this is such a small board. So you do want to make sure that anytime you do, analog input, that you're making sure that you're on an analog input pin. And so I ended up using A2 here because I knew I could get an analog input. Now this also had to be sorted out with my buttons because the deep sleep button in particular needed to be mapped to a pin that could work with a real-time clock, because whenever you go into deep sleep mode, it shuts a lot of things off, and a lot of your GPIO pins will not be able to wake the ESP32 out of deep sleep. And so one of the things you can look up is in the resources on the wiki for the Xiao ESP32-C3 is the pinout sheet. And so in the pinout, it actually gives you all the pins and their different names under different schemas. And what you want to do is, if you're needing a Wakeup pin, it has to be one of these that has a label with an RTC on it. If you don't use an RTC enabled pin or a power domain pin here, the rest of the stuff can get shut off. And so again, you can't wake it up from a button pressed on one of those other pins. Now you could still do an internal timer or something like that. But I had to make sure that I used one of these RTC pins. And so I believe I ended up just using GPIO 2 for my Wakeup pin, which ends up being the D0 pin on the board, because GPIO 0 and 1 are not externally available. And that's one of the other issues, is not all of these are externally available because they get used for other things internally. So I ended up using D0, which is also A0. That is basically this first pin in the upper left. That is where I mapped the Wakeup button. Again, just because it needs to be an RTC-enabled GPIO pin. Okay, so then we get the BLE started, we add all the services and characteristics, and now we get into the main loop here. Okay, so we set up the central so that we know whether or not we are connected via Bluetooth. We do some data checks. We've got the serial print interval to make sure that we're not overrunning our HX711 data feed, because we only get data so often for that. It's updating about 80 times a second max. And so then we've got the if load cell update, new data ready equal true statement. And this is just to make sure, hey, is there new data available from the scale? If so, again, now we run into essentially the same routine from the other video. So again, if you want to know how that read data routine runs for the ADC and reading from the scale, watch the other video because it goes through that. Significantly different in this setup is the unit state, and this is basically a toggle, a Boolean variable that flips between 0 and 1 in case I want to read out in grams or ounces. And so if it's set to 0, it reads out in grams. If it's set to 1, it comes down here, and it does just a simple scalar to change that value over into the appropriate value for ounces reading. I don't plan on using that much, but I thought, it'll be interesting to include. Next up was the indicators for battery level. And so here I've got the battery level coming in and also whether or not we are connected to BLE. And if we are, it updates the readout to say, hey, you're updated to BLE. Now, if we're not connected, it's going to say no BLE, and that's the only thing really that's left in this section of the code. Again, it's just setting up the display, and this manages the readout of the mass and then the indicator variables on the screen. Next up, we've got a simple digital read on the tare button, and if it gets pulled low, we run a little tare function. If I scroll down, the tare function is just running the no delay load cell tare function that comes out of that include. Next up, we've got, again, another digital read check. And here's the little debounce. If you're looking for a debounce function, this is just a little debounce routine that makes sure that a certain amount of time has passed before it will allow that button to change its state. If I go back up to the top, I've got the debounce time set to 50 milliseconds, and that, again, just keeps that button from switching too fast. If you find that the button isn't sensitive enough, you can lower that debounce value. If you find that you're getting too many false switches, you can increase that debounce time. But it just makes sure that you're not switching too fast so that you get solid switches rather than, electric noise or anything in that process. Okay, next up is the sleep routine. Okay, and so this is watching the sleep button and it's checking, does that pin get brought low? Because the way it's set up, the pin, whenever it's pressed, gets shorted to ground. And so you have to have either input pull-up resistors internally or externally on that switch. That's the way I've got it wired up. So what I'm looking for is anytime that switch connects to ground, then trigger. So the top here is just display stuff, so don't worry about that. The real routine is here. So if that button gets brought low, then here's the command to put the microcontroller into deep sleep with a GPIO pin wake up. Now there are various different commands depending on how you want to wake up out of deep sleep. If you want a timer, there's a different command. If you want, I forget, there's some other different ways that you can wake the thing up. But I wanted a pin wake up because I want to do it with a button. So I wanted to do deep sleep, and so this is the command for the ESP, right? ESP deep sleep enable GPIO wake up, and it gives you a function blurb about how this thing works up. And here you can see only GPIOs, which that's their little typo there, which have RTC functionality can be used in this bitmap. All right. So there are two sections. One, you have to map, and so this is saying, hey, make this pin the one that wakes it up. With this bitmap thing, I'm not 100% sure what that is, but this is what I put in. Set pin 2, GPIO pin 2, to be set to 1. Basically, it's the pin that I want to use to wake up. And then this is how do you want that button or that pin to work. And so the ESP GPIO wake up GPIO low says when this pin gets taken low, put this thing to sleep. Okay, now you would think that would be all you needed. It's not. Okay, that just sets up the pin itself. The second part is now I'm turning off the display. So that's all this is. This is just saying, hey, turn the display to power save mode. Then you have to say, okay, now go into deep sleep. So ESP deep sleep start actually puts the thing to sleep. If you put it to sleep without having a wake up, it won't wake up. All right, you would just have to reset the device because it will not wake up otherwise. So you have to have the wake up stuff set up how you want it to wake up. Then you tell it to go to sleep. Now there's a delay right here. And this is actually what makes this whole thing work, because if you remove this delay and you put that thing to sleep, it'll just immediately wake back up. And I don't know why, except all I can think is it takes some time internally maybe to get this thing started. But if you don't put any delay, it won't stay asleep. It just immediately re-wakes. It's almost like a reset button instead of a sleep button. So I don't know that you need a full second delay, but you do need some delay. I think I went as low as like 100 milliseconds and it still worked, but you definitely have to have that delay or it'll drive you crazy. This is why I thought that I had a problem with the input pull-up resistor that is internal, because it just wouldn't work. And I was looking at the code, and I was looking at all their documentation, and everything said that my code was right. Like I couldn't find any errors at all. And I did all kinds of things. You know, I'm not going to go through all the different ways I tried to debug this thing, but I had no idea what was going on. And then randomly on Reddit, I found a comment that somebody was talking about this. They're like, oh, I put a delay in and it worked. And I tried it, and boom, it just perfectly worked after that. It was infuriating. But that's all you need to do. And just because I want to give some kudos, this is the post, right? This WChris63 on Reddit. This is the post that actually helped me figure this out. Now, this is actually about light sleep, but again, I was reading anything trying to figure this out. And right here it says, found a reference that talks about this. In their case, the ESP returned from sleep immediately. That was the problem I was having. And it said, well, they inserted a delay, and that's it. And so again, this is not the same thing, because this is for light sleep, but it is necessary, right? You just put in a little delay and boom, the thing magically worked. So you actually don't need any other setup to wake the thing up, because with this line, that power button, or rather sleep button, will automatically now wake it up whenever you push it. So this is the entire routine to put the thing to sleep. Next up, we've got our little section to receive commands from the Bluetooth app. So we're reading if the button characteristic gets written from the app side. And so it reads that value. If the value comes over as 2, run the tare function. If the value comes over as 1, this is to start logging, and I got a little typo, that should be logging, in the app. And so all that does is it flips the log state. Okay, and so the log state will flip from 0 to 1, whether or not we want to be in logging mode or not. And so all that does is it triggers right here. If the logging state is 1, then we're doing logging. And so we've got a little delay interval, which is non-blocking, that says, hey, if the time since we've last done a data transfer is longer than our log interval, which I've got set to 250 milliseconds, then write the BLE mass variable, which is our newest mass reading, over the logging characteristic, which is that second characteristic that I had set up. And then just update our timer. That way we know that we have now updated the log again. And so that's all that you have to do to make sure that, hey, I'm getting mass written over, 4 times a second. You can just update this log interval, and it will adjust how frequently you're sending data on that log interval. The last piece that I haven't talked about is the internal battery level. So again, I'm reading that through a pin. It's not internal. It's actually an external thing. And I found this code from, again, a post on a forum somewhere. And this is from the SEED Studio forum, and that's where I found this. And so again, I just want to give proper attribution to whoever figured this out. And this is from this, MS Fujino, I don't know if that's what they're going by. And they're the ones that I got this idea from. They use 220K resistors. I think I used 200K resistors. And they wired theirs up on the board itself, whereas I'm feeding them in. But again, they're just tying it to one of the analog read pins. And that's how you get the voltage in, because there isn't an internal pin to do this. Now, whenever you do this, you do have to map the values of the voltage to a percentage if you want some sort of life estimate. And so, like, if you just go out and you Google 4.2 volt battery table, you'll get like all these different, life tables that people have created. And I don't really remember which one I chose, but I ended up grabbing one of these and I just mapped the values into Excel, and I actually used the Excel charting function, and you can actually back solve an equation that will fit a line. And that's all I did. So whenever you come in here and you see this battery level little math function here with the powers, this is basically a cubic term, a quadratic term, and a scalar term here in the math. I mean, this is just a back-solved formula from one of these tables that gets pretty close, and I think I may have tweaked it just a bit. So all I'll say about that is Don't take this as gospel that the battery percentage that it kicks out is actually how much life you have. I wanted something approximate, and I do think it's approximate, but it's definitely not absolute. I will say, as far as battery life, the 1000 milliamp hour battery that I've got, it seems to last a long time, like 8 to 10 hours. So battery life didn't really seem to be a problem, but you know, if you're getting down under 20%, at least this thing will let you know, you're roughly in the range where you should probably recharge. But all this is, again, just taking a reading. It's doing a little float and doing the adjustment because of the way it gets read, and we're using a voltage divider and reading the middle, so nothing special about that. And then it just kicks out the battery level that is then feeding into the screen. And that's really all there is to the Arduino code. So now let's flip over to App Inventor, where a lot more headaches occurred. Okay, so here we are in App Inventor, and I've got my screen set up. Now, again, as always, whenever you're setting up a screen, you're just pulling elements over here from the left on the screen and just doing your arrangement. So there's not a lot to go into about this, but there is kind of one unique thing, is that technically, my app only has one screen, and this was something I learned in the process of making this project. You can have multiple apparent screens, or they're called virtual screens, but only actually have one screen, and this is actually pretty important because in MIT App Inventor, you can't easily share data and stuff between screens. So if you actually had multiple true screens, it'd be kind of a pain in the ass to get data back and forth between them. So what you do is you do these virtual screens. And the way this works is I've got a logging screen and a home screen. And if you look, my logging screen is currently visible. But if I turn it off and then come up here to the home screen and make it visible, this is the default screen whenever you open the app. And so what you do is you set up a block, and right here you can say, well, when the app basically initializes, set the home screen to visible, set the logging screen to, visible false or invisible. Then you have a button, and so if I go back here to Designer, when you click on the logger button, all that button does is it just changes what's visible on the screen. So right here you see when the logger button gets clicked, just set the home screen to invisible, set the logging screen to visible. And so that was a nice little trick that I learned in this process. Just a lot of helpful stuff on the internet about MIT App Inventor. There's a good community out there. And so that was the thing that I learned for that. One of the other things that I figured out on this one is this is not real great for displaying stuff, and even this is probably necessary, is actually viewing stuff in like monitor size, because if you leave it on phone size, it's really small and your buttons look like they're going to be messed up. But this is actually more what the app looks like when you open it. The buttons are visible, everything's visible. So anyway, I wouldn't worry too much. You got to be careful at least about how much weight you put on the actual view that it gives you. And that was another thing that I learned in this project, is this is not actually what these things look like whenever you open up the app. So it's always important to run the real thing. Now, another last thing on layout, to get these buttons spaced, I'm actually using a whole bunch of little labels all over the place. And so I've got a whole bunch of just blank, empty labels just to give me padding. And I really wish they would add the ability to pad buttons and stuff in this app, because otherwise the buttons all touch and it's really ugly. If you look in my other app, the interface is pretty bad, and that was one of the new things that I learned in this project, was just adding these things. But yeah, I do wish they'd add some padding features to the buttons. So let's get over into the blocks, and if I zoom out, you'll see there's a whole lot of crap going on. Now, a lot of this is similar to the other app, so I'm going to try to focus on the new things. So basically, when the app starts up, again, you're just going to be on that home screen, and that's just to do the Bluetooth connection. So whenever it opens, it says scan for device. You scan for a device. Once a device is found, it updates the picker list. And then that list picker, whenever you click whatever device you're trying to connect to, that's what will then be connected. Then when the device is connected, at this point, we have to register to receive data. and we are trying to receive float data for the mass characteristic, and so you've got to have the right service and characteristic UUIDs there. And so you're going to register to receive these floats, and when the floats are received, I'm going to display them on the main display. That is the main function of the app, right? The main display, that is how it gets its data, okay, is the register for floats, and then when floats are received, set the readout text to the float values that you got via this characteristic. Now, it's a lot more complicated because now there are two float characteristics coming over. One of them is for the logging data. So what I've done is I've basically had a bunch of if-then variables. And so what this says is, look, when you receive floating values, if they're from the regular characteristic, just put them on the screen. Otherwise, if they're from the logging characteristic, are we in the logging state, right? And if we are, then we are going to add those to some internal data. Now, what this is not a database. This is just a list. And so this is where, again, this was a total pain to get all this set up. I looked at a lot of stuff on the App Inventor forums. I talked to ChatGPT. I did all kinds of things to make this stuff work. And so here's how you build CSVs. All right, so first, I'm going to name this data series with a little text entry, and that's the shot name block, or rather box. So right here in the middle, this is the shot name. So you type in a name here. It's going to pull it in, and that is the first part of a text string that we're about to build. I have to add a comma because we're doing comma-spaced value, CSV. Then I get a timestamp. Now, in order to get a timestamp, I actually over here have embedded in a different process. Basically, once you click the logging button, it generates a timestamp. And it has to call from an internal clock, and it sets up a timestamp. So you actually have to have over in Designer, if I scroll down to the bottom, a clock. That way this thing can keep track of time to generate this timestamp. So the only reason I'm using a timestamp is that I know what time the button was pressed. This does not time the data, it times the entire series. So this timestamp value for this data series is a constant value just like the name. So these two things in the output file will be the same name. And the only reason I did that is this kind of gets auto-generated, and if you accidentally generate two strings with the same name or two series with the same name, this would allow you to differentiate between them because they would have to have been created at different times. And so this keeps each data series unique, and it's also a good reference so that if you ever get lost or forget what you did, you'll at least know when it happened. So the next thing is to pull in a variable called shot time. Okay, now shot time is going to be an individual data time. So every data point will get an individual shot time, and every data point just sequentially gets another 0.25 added to it. And the reason why is I know that every one of these float values came from the Arduino or microcontroller side, and it's only pushing data every 250 milliseconds. And so I'm relying on the microcontroller's timing of pushing the data. It doesn't matter when I receive it. I know every sequential data point is 0.25 milliseconds after the last one. So I'm attaching that to each data point and then iterating that time value up a quarter of a second so that the next time it comes through this loop, it gives an extra quarter of a second. Okay, then we just format and then the float value. So there's going to be 4 columns to this CSV string, but it puts them all in one text string and stores it as an item inside of a list called internal data. So then I can reference internal data, and that's a list of all my all my data series data. And now at the same time, I want to add the log data that is live coming in to the chart, and so you've got to have a chart. So what we do over here is we bring into the logging screen, you've got a chart. And then you also have to add chart data to the chart. So I've drug over a chart, I have drug over chart data, 2D, into the chart. So that gives me access to add X and Y entries. The X entries are the shot times, and again, these are just iterating at 0.25 seconds every data point. And then the y variables are, well, the float value that I just got in this loop. And so that's how it live updates the chart. So basically, this process has handled updating the display, the main display, and writing data series to an internal data list, and updating the chart on the screen live whenever we received log data. The next section is what to do whenever we click the Write File button. Okay, so in the designer over here, we've got this Write External that's going to write an external file. It's going to use the file name in this text box here to the left, and that's what it's going to name your file, and it's going to make it a CSV. It's going to add .csv to the end of whatever you type here, and it's going to put it in your phone's download folder. So whenever you click the Write File button, here's what it's going to do. It creates a new little variable called CSV content, and that is going to be a little chunk that it's going to write out to the CSV file. And then it says for each item that is in your internal data set, and so that's going to be one of these strings, take that content, add this /n to the end. And the reason is this is the character string that tells anything that reads a CSV file where the row breaks are, right? So this is a line break. And, you know, the way I read it is this is how you know that you're going to a new line. And so it says put this at the end because this is one row of data. Then write that to an external file, right? So we get the content, and we're doing this for each item in the list. So it's going to go item by item through CSV content. Every row gets a little row break at the end, and then it puts that in this file. And the way it builds the export is put it in the download folder, pull the name from the text, put .csv at the end, and it will just write this thing out row by row. This does take a little bit of time, so whenever you click the Write File button, it will take a good 10 to 15 seconds, maybe more, for the file to actually show up in the download folder. Now, whenever you click the Read File button, I'm going to call this routine that's called Read CSV that I've built right here. And so the Read CSV routine, and actually I don't even need this, I could just drag this whole thing up and put it in here and get rid of the routine. I don't know, I was following like a tutorial, something ChatGPT told me, I don't know why I broke it out like this. But all that's going to do is it will read from the file that we have written in the text box. So again, you can pull a different file. You write the file's name that you want to pull without a CSV on it. It grabs that name and it reads from that file. When it sees that there is text coming in, so when file 1 has text, then set the internal data set. You're going to write that over with the text that you get in, and you create items in that set by splitting, again, on that /n. So your internal data set does not have the row break data in it. It only has the actual row data, but not this line break. And when you export it, you write this line break, and when you import it, you're splitting the text at the line break, so it just kind of gets eliminated during that process. And that's how you get data back into your internal data set. Now at that point, if you want to view an internal data set on the screen, what do? Well, you read it in from an external file, then you have to load it so that it can be selected, basically. And so if you click the Load Series button, it creates a little list, and what you have to do is you've got a whole bunch of data potentially in this file, and you want an individual series of data to plot on the screen. Well, you need to get the names of the series of data, and they're all in that first column that we created over here, right? We have the shot name, that's what I'm calling the series name, as the first item on every row in this file. But, you know, the shot name can appear on multiple rows because each row is actually a different set of weight data. So I have to filter all of that data in that first column into a unique series of IDs to select from. So we're creating a list to capture those names, all right? So for each item in internal data, we, write it into a list, then we split it at commas to get each individual item, and we check to see if the name that we pull, so we're looking at each row of data, looking at the first item, so this is going to be the actual shot ID or the series name, and we say, is it not already in our list global shot IDs? If it's not in there, then add it. All right, so what this does is it makes sure that you're not duplicating names, and this is how you filter that into a unique name list. And then we set our list picker, which I'm calling series picker here, to that list that we just generated of these unique data series names. And so the functionality over here is we read in a file, we click the load button, and then we can select an individual data series with this select button. And once we do, it will put the data on the screen because it knows exactly what data to pull out of that file. Okay, I've got some other stuff, just, it's not organized maybe as carefully as it should. If you click the back button, it just goes back to the home screen by changing the visibility. If you click the tear button, it sends the order over to the microcontroller to tear the scale. Okay, so the things that we've got left is the start routine. But since we just covered generating this internal data of series names, how do you display them? It's over here. Okay, so once you collect and you load up this data, right? So we've put all these things into the picker so that we can pick some stuff. Then if you click the list picker, which is how we select a series, it's going to pull up all the data in these global shot IDs and figure out what to do with it, right? It has to pull in the data from the internal list and then put it on the screen. So the first thing it does, it says, all right, you select something from this series pick, from this selection picker button, right? Whatever your selection is, run it through this filter data process. All right, so what the filtered data does is it's going to go in to the internal data that we have loaded in from our external file. It's going to bring in the name that you selected with this list picker element, and it's going to go through and it's going to grab all the rows that match that title, okay? And so it does that by setting up some little internal variables, some local variables, and it's going to split those items up at commas, and it's going to grab a few of them, all right, into a little data set. It's going to grab the name of the series, and it's going to grab the time, the shot time, and the mass reading from each one. Okay, so that's what it's going to return. It's going to return all the data entries, right, with the name that you asked for. That's what this little routine does. Okay, once it's got that, it clears the display, it clears the chart, it sets the chart label to whatever selection you made, which is going to be the series name, and then it pulls the filtered data that we just got out of this routine, and it puts it on the chart, right? It splits it at the commas. And again, the reason why you're seeing all this join and split is because these internal lists, I'm keeping the row as an individual item. So I need all as one text string, and I'm just using that CSV format because it's easy to maintain the read-write and everything is consistent. And so whenever you're going to use the data, you have to split it up. Whenever you're going to store it again, you have to link it together with commas. And so since we want to display it, we split everything at commas, and then we display items 2 and 3, which end up being the X variable is going to be the time, and then the Y variable is going to be the mass. And so that puts it on the screen, and that's how it does the internal display. Because of the way this is written, you can redisplay items that have never been written to external files because that internal data set is kept until you either close the app or until you import new data over it. And so you don't have to read from an external file. If you've been working and you record a few different data series, you can pull up any of them. But as soon as you read in an external file, it's going to overwrite that. Okay, the last thing I'll cover before we get to the biggest, most difficult piece, the logger button. If you click the logger button, that just changes screens. We've got a little notification if Bluetooth ever gets disconnected to send us a message. And then what happens if we click the disconnect button on the main screen. So that's all pretty straightforward. But then we've got the last routine to cover. What happens when you click this start logging button? Because we've got a couple things that we need to do. we need to send a message over to the microcontroller to turn on the logging function and start sending us logging data. When we click that button, we check, are we already logging data? Okay, so if our global log state is set to 0, right, because what happens is when you click this button, we want to make sure that we're not already logging. If we're already logging, then we know we want to stop, and so we want to flip this button from start to stop, and so the same button can both start the log and stop the log process. So what I'm doing is I'm checking for the state. Are we logging? Right? And if we're not, then check to see if we're connected to Bluetooth. If you don't have this, the app will crash, all right, because it will try to do something that it can't do. So if we're connected and we've clicked this button, we haven't been logging, so this we know we are starting a log. Check to see if we're connected to Bluetooth, then right over the integer 1, and some people do bytes instead of integers. I don't know if there's a difference, but I'm just writing an integer. It hasn't seemed to be a problem. I'm sure there's probably some efficiency somewhere, but I don't care because it's not a problem yet. I write over a value 1, and this turns the logging on the microcontroller, so it's going to start spitting data back at us every 250 milliseconds for the log. Clear the chart, call a global timestamp, and this is going to get put into the log. Set our shot time to 0 because we're starting from now. Now is time 0 on this data series. Turn our logging state to 1 because we are now doing our log, and that's going to trigger this process over here. All right, we're going to start collecting that data and putting it on the chart and writing it to our internal list. Turn that start button into a stop button, change the color. And so when you click the start button, it starts logging and the color of the button changes and it starts saying stop, because if you push the button again, we are now not in log state 0. And so it says, well, if we're not in log state 0, we can only be in log state 1. So set the log state to 0. We're no longer logging. We're turning things off. Set the button back to start, setting the button color back to green. And if we are connected to Bluetooth, then send that log item over and turn the logging off from the microcontroller. And that's how all the code works. There's some other variables that I didn't talk about, how they got created, but that's no worries. If you're interested in this, all the code is out there, and I've covered the more difficult pieces and why things are the way they are. This, it looks very simple whenever you see it and it's set up to work. It took a very long time to figure out how to read and write these files correctly and how to make the internal data lists seamless so that they all worked and didn't cause anything else to crash, because they really do all need to be formatted consistently, and these joins and splits and everything really have to be handled correct, or you will run into a lot of problems. I am pretty happy with the way this ended up, because if you'll notice, I am not using TinyDB. There is no database. This is all done internally with lists and writing to an external file. And you can take that file and go do other stuff with it. If you want to look at your data in Excel or another data analysis program, it's going to be really easy to use because it's just in a CSV format. And so I didn't have to figure out how to export TinyDBs, and I didn't have to worry about multiple databases. As it turns out, you can just use lists. And if you join your stuff into rows with commas into one string, you can just store all of them in lists, and you can make it work. So that is how the code works. If you've got any questions, as always, feel free to leave a comment, and I'll try to explain anything that's left unclear. And there will be a link to the source code in the descriptions that you can look at all this.